Alright, so we're going to do another problem using Gauss's law. And this is 1993 from the E&M test, problem number 1. The solid non-conducting cylinder of radius r shown above is very long. It contains a negative charge evenly distributed throughout the cylinder with volume charge density rho. Point P1 is outside the cylinder at a distance r1 from its center, C, and point P2 inside the cylinder at a distance r2 from its center, C. Both points are in the same plane, which is perpendicular to the axis of the cylinder. Okay, now for part A, they give us a cross-sectional diagram with P1 here, and then you have our non-conducting cylinder. The center C is here, and P2 is here. And they ask us to draw the vectors to indicate the direction of the electric field at points P1 and P2. So at P1, the electric field is going to be going here, and at P2, it's going to be going here because they're going to be drawn towards the center. Now for part B, they're asking us, using Gauss's law, derive expression for the magnitude of electric field E in terms of R, little r, big R, rho, and the fundamental constants. And the first case is asking us when little r is greater than big R, which means we're outside the cylinder. So using this, we can use a Gaussian cylinder with radius little r and length L. So the closed integral of E dot dA is equal to Q enclosed over epsilon naught. So then we can use closed integral of E dot dA is equal to E times integral of dA. And since we're using a cylinder, it's equal to E times 2 pi RL. And then Q enclosed, since we're using a Gaussian cylinder and since there's constant density rho, we can say that it's equal to rho times pi r squared L, because we can use the area. So then E times 2 pi RL is equal to rho times pi big R squared L over epsilon naught. So we can cross these out, and we get E is equal to rho big R squared over 2 epsilon naught little r. And this is for outside the cylinder. And when the problem also asks us to find inside the cylinder, and we can use this where r is less than big R, so this is inside. So we can use the same Gaussian cylinder with radius r and length L. So we're using this, we have E dot dA, and we can, using our other problem, we know that this is E times 2 pi RL. The only thing that changes is that Q enclosed is going to be rho times pi little r squared L, since it's going to be inside the conducting cylinder. So using that, we have E times 2 pi RL is equal to rho pi r squared L over epsilon naught. You can cancel these out and this, and you get E is equal to rho r over epsilon naught. And that's our problem.